Our project title is An Efficient Data Security System Using Reverse Room Approach. Our main objective of our project is to enhance a system for secret data communication over unsecured channels based on image encryption and data hiding technique. In order to preserve image quality during recovery, reverse room approach is used. Reverse room approach is used to reserve space for embedding secret data. A part of the image is reserved for embedding the data and remaining part is encrypted using chaos encryption. After an encryption, the secret data is embedded into the reserved coefficient using adaptive LSB replacement technique. In the existing method, the confidential data is embedded into the image using bit modification technique. This leads to poor data hiding and has more distortion, which degrades the image quality. In the proposed system, it used to encrypt the image and confidential data using chaos encryption. The confidential data is encrypted into unreadable form using lifting wavelet transform. After encryption, the confidential data is embedded into the image pixel coefficient using adaptive LSB replacement. This technique is more confidential and prevents outsiders from hacking. Input image consists of RGB plane. Before processing an input image, the B plane is separated. It is done because B plane is least sensitive to changes, so we can embed data into it. It remains the same as of the original image. The input image is divided into non-overlapping blocks, non-overlapping 8x8 matrices. The LWT decomposes the images into different subbands, namely LL, LH, HH, and HL for embedding the messages in the pixel coefficient of subband. After decomposing the image, the suitable coefficient is chosen and it is reserved for hiding the data. The remaining coefficient is encrypted using chaos encryption. In the same way, the secret data is encrypted using chaos encryption. In the data concealment block, the confidential data is embedded into the reserved coefficient using adaptive LSB. Finally, we get the STIGO encrypted image. In the data extraction module, the secret data will be extracted by using relevant key. By using the decryption key, the image and text will be extracted from encryption to get to the original information. Lifting wavelet transform. It is used to reserve space for hiding the data. LWT decomposes the image into different subbands, namely LL, LH, HL, and HH for embedding the message in the pixel coefficient of subband. Basically, image has two subbands, namely low frequency subband and high frequency subband. The low frequency subband usually contains the visible information, whereas the high frequency contains texture, edge, and noise. The secret data is embedded into the high frequency subband because it is least sensitive to changes. The slide shows the stages of LWT. Here the input image is divided into low and high frequency subbands by vertical decomposition. By further proceeding, the horizontal decomposition will divide the low and high frequency into low high and low high frequency, which yields in approximated and detailed coefficient, that is LL, LH, HL, and HH, where L represents low pass filter and H represents high pass filter. This is the formula for obtaining the H and L value. H value is given by Cout minus Ce and L value is Ce plus H bar 2. And by row wise processing to get LL, LH, HL, and HH. LH is equal to L odd minus L even. LL is equal to L even plus LH by 2. Stages of work. In the first module, data and image analysis for encryption. In module 2, encryption of data and image and embedding them for transmission. In module 3, retrieval of image data and performance analysis is made. Input and transformed image with encryption. The first figure shows the input image, whereas the second figure is the B-plane separation of the input image. Third figure is the transformed image. Chaos encryption. This method is one of the advanced encryption standard to encrypt the image for secure transmission. It encrypts the original image pixel with values with encryption key values generated from chaotic sequence with threshold function. It is very useful to transmit the secret image through unsecured channels securely, which prevents data hacking. This is the chaos encryption flow. The chaotic sequence initiate constant factors is used to initiate the values for x and u. The chaotic sequence generation is done by the help of the formula xn plus 1 is equal to u into x 1 minus x, where u is the scaling factor which ranges from 0 to 4 and x is the initial factor which ranges from 0 to 1. Threshold function is given by 1 bar 255 is less than xn plus 1, which is less than 1 plus I plus 1 bar 255. By knowing the input image and the thresholding function, the bit XOR operation is performed between them in order to find the encrypted key. By using the encrypted key, the image is encrypted. The output of the chaos encryption is first figure shows the cover image and the next figure is the encrypted image. Adaptive LSB embedding. The first bit of message is embedded into the LSB of first pixel and the second bit of message is embedded into the second pixel. The resulted Stego image, which holds a secret message, is a 8-bit grayscale image. The quality of the image, however, degrades with the increase in number of LSBs. This is the algorithm flow of LSB. From the decomposed image, the high frequency band is selected, which is given to the LSB technique, and the secret data is also given to the LSB replacement. Here the LSB replacement consists of a message bit which is given by 00110100 and coefficient is 00011010, and the payload for this is 3 bits per pixel. Coefficient before embedding will be 00011000. After LSB replacement, the coefficient will be 00011001. By applying inverse transform, we get the Stego image. Data extraction. The extraction process is opposite to data embedding. Pixel coefficient and embedding rate are used here for extracting of data. The lifting wavelet transformation will be performed to Stego image to find reversed space and select coefficients which are used at the embedding site. Finally, extracted secret text data is in the form of ciphertext and then converted into plain text using decryption process. This is the output. Whereas figure 3 shows the encrypted Stego image and figure 4 shows the recovered image. The performance of the technique will be evaluated by mean square error, peak signal to noise ratio and correlation coefficient. Correlation coefficient is the similarity between two different images with their intensities. The correlation coefficient is given by this formula where U1 is the mean of F1, U2 is mean of F2 and F1 is the cover image and F2 is the encrypted image. The peak signal to noise ratio is given by 10 log 10 255 square by MSC. The mean square error is given by this formula. Here the M and N represents the number of rows and columns and Aij is the input image and Bij is the embedded image. Sample text encryption. Input text is given as how are you and the ciphertext is this and decryption text is how are you. The performance metrics for the sample text encryption are mean square error is 0.0172, peak signal to noise ratio is given by 65.7725 decibel and correlation is 0.0019, Elapsed time is 7.7752 seconds. The advantages is more security than previous method, data hiding capacity is high, less degradation in image quality during recovery. Applications are, it is used in research institute, medical information protection, and it is used in secret data communication in defense. This project presents the protection of image quality and hidden data during transmission based on the approach of reverse room technique and chaotic crypto system with LSB based data concealment. The system generates a stereo image with less error under maximum data hiding capacity. Finally, the performance of the system was evaluated with quality metrics such as correlation and SNR factor.